In this question, we're given two Carnot engines using the same cold reservoir at a temperature of 275 Kelvin for the exhaust heat. So this is basically T cold. Each engine receives 1,450 joules of input heat. This would be QH. The work from either of these engines is used to drive a pulley arrangement that uses a rope to accelerate a 125 kilogram crate from rest along a horizontal frictionless surface, as shown in the figure. With engine 1, the crate attains a speed of 2 meters per second, whereas with engine 2, it attains a speed of 3 meters per second. So we have some conceptual questions to discuss first. With which engine is the change in the crate's energy greater? So obviously, like the change in energy is gonna be a change in the kinetic energy. This is the total energy of the system. So this is just K final minus K initial, and both crates start from rest, so it's simply just the final kinetic energy. The crate has like it's a constant mass, and the velocity is the only factor. And you can see how with engine 2 we have a larger speed attained, 3 meters per second as compared to 2 meters per second. And thus we can say that the change in energy for engine 2 is greater than that in engine 1. In the second part, we want to see which engine does more work. So let's try to link the work to the given that we have in this question. We are given T cold and QH, and we are given the speeds. Essentially, from the speeds, I guess we can find the work done, because the work done is just equal to the change in kinetic energy. So knowing that W is just equal to delta K by the work energy theorem, and seeing that the work done is just due to the engine, there are no other forces, and delta K2 is greater than delta K1, then W2 is also greater than W1. For which engine, this is in part 3, is the temperature of the hot reservoir greater? So we are given T cold, we are given QH, we can find W as well. Let's try to check some expression for the temperature of the hot reservoir. This is TH. One thing I know is the efficiency, which is the work done divided by the input heat, can also, in this case, be written as 1 minus T cold over T hot, since we have a Carnot engine. What we're interested in is TH. And if I actually rearrange the equations, you will get TH to be equal to TC over 1 minus W over QH. So TC and QH are the same. Whereas W2 is greater than W1. The result will be that TH for engine 2 is going to be greater as well. You can see it by looking at the expression we have here. If W2 is bigger, then 1 minus W2 is going to be smaller, and a smaller value in the denominator will give us a bigger value for the whole fraction, right? Now, in this part, we also want to find the temperature of the hot reservoir for each engine. So I'll just write TH2 to be equal to T cold over 1 minus W2 over QH. T cold is like the same for both engines. It is 275 Kelvin. And W, I can write it as the change in kinetic energy, which is the kinetic energy itself, since, like we said, W is delta K, and delta K is K final. So this can be written as half mv2 squared divided by QH. So I'm actually just starting with T hot for engine number 2. The mass of the crate was 125 kilograms. The velocity for engine 2 is 3 meters per second. And QH for both engines is 1,450 joules. So you can find pH for engine 2, it's going to be 449 Kelvin. A similar calculation for engine 1 will give you 332 Kelvin.